Hi, welcome to my channel, and I'll be going over some interesting subjects, mainly in chem, but I might do other subjects too occasionally, depending on what I'm thinking about doing this year. But I guess for now, chemistry is going to be my main focus. Let's start with radiation, because it's kind of fun. It's really interesting, isn't it? Um, so radioactivity was first discovered by not by Madame Marie Curie. This is my Marie Curie, but actually by some other dude. His name was Henry Becquerel, and he had the sickest beard ever. So this is my Henry Becquerel. And just 2 years prior, so it's whatever. And essentially, what it defines is it actually describes how atoms that are unstable will decompose. This happens because we have more nucleus, too many nucleuses, or too many protons or neutrons, aka our nucleons are, let's call it, unbalanced, because I feel like a lot of chemistry is balancing stuff. So it means that, basically our nucleons are unbalanced. All of this terminology right here, it sounds super confusing and super hard, but I promise you it's actually a lot more simple than it is. I'm sure we both know, everyone knows what a proton is, right? It's the positively charged thing inside of an atom. A neutron doesn't actually stand for negative; it just stands for neutral. So it's a neutral charge. Now, if we look at like a periodic table, I don't have one right now, but I'm just gonna draw a sample right here. Let's say hydrogen. What we know is that it's gonna have an atomic number 1 and an atomic mass 1.01. Now, we all know that this one stands for the atomic number, which is also how many protons. How many protons? This one, you may know, is atomic weight. Atomic weight, and that essentially describes how heavy we can expect our element to be. However, you do have to note that this is a weighted average of all the many different isotopes. So what does that even mean? Okay, well, let's really quickly sort of dissect. The element. I don't really like. Let's do carbon instead, because hydrogen is a little hard to exemplify. Carbon has an element number of 6 and a weight of about 12, just like 12.01. So it's a weighted average of all of our different isotopes. So carbon has a couple that I can name off the top of my head. Just kidding, just 2. And basically, a weighted average is how much of it is present in the world. Lots of a little more advanced chemistry that I might go over in a different video, but not the topic. The thing we have to note about it is that since we know that electrons are about basically massless. Because we know that electrons are basically massless, and protons weigh about 1 AMU, actually exactly 1 AMU, I should say. 1 AMU, that means that neutrons must also weigh 1 AMU. Because if we look at like carbon 12, it's going to weigh 12 with 6 protons. Since electrons are basically massless, that means that neutrons, we got 6 of them. Okay, so what happens when all of this is messed up? Let's talk carbon-14. Carbon-14 is considered radioactive, right? And when we think about this word, we might think about like uranium, stuff that glows green and makes big things go big boom and craziness, right? But actually, basically everything can be radioactive. Potassium in bananas, that's pretty radioactive. And you know, carbon-14, it's inside you, it's inside dinosaurs. That's actually how we figured out how old dinosaurs are. So what is an isotope? I feel like I should probably define what an isotope is really quickly. So an isotope is basically different ways one element can be found in nature. So when we think about this, let's go back to my carbon-14 example. All right, there's carbon-12 and carbon-14. Carbon-12 is a relatively stable because, you know, it's 1 proton per 1 neutron. You know, because it's carbon's element number equals 6, so 6 protons. 12 minus 6 equals 6, so then we have 6 neutrons, 1 to 1. You know, neutrons are basically like packing peanuts, right? So, yeah, but carbon-14, it's going to have 6 protons, but 8 neutrons. Why is that bad? If you think about it, it's kind of nonsensical. Why would having too many neutrons be bad? I mean, when we think about it, protons kinds of make sense. If you try to put 2 positive termina of a magnet together, they will repel each other, right? So if we think about putting 2 protons next to each other, they'll repel each other in instability. But neutrons are often thought about as like packing peanuts. They just are there kind of as a buffer between our positively charged protons, right? So it doesn't really make too much sense, but the way I like to visualize it is, if we have too many of these packing peanuts in a box, say this is my box, and we have just too many packing peanuts, eventually the box A will not close, and then B just start to overflow, right? So that's how I think about neutrons. If we have too many neutrons, we'll have too much energy inside inside our nucleus, and it'll explode. Okay, so too many protons. Wow, I just completely butchered that. Too many protons and neutrons will cause instability. Because, sorry, I should really think about writing legibly. Because it's got lots of NRG. Energy, right? This is a really important thing. This is a key takeaway to take away from this video. If you learn nothing else, maybe this. I have a couple other really important things to think about, but that's okay. These are one of them. So, and basically, radiation is nature's way of dealing with imbalanced proton-neutron counts. Do note that we do have a couple types of radiation. There's alpha particle radiation, beta decay, there's like gamma rays, and then we have a couple types of radiation in general, which is alpha decay, beta decay, positron emission, and electron emission, right? So let's basically go over exactly what happens in each of these scenarios. So starting with alpha decay, what happens in alpha decay is we'll have our unhappy nucleus, and it'll shed what's basically a helium. So it has a mass of 4 with 2 protons in it. And this happens in an effort to get happier, to become more stable. A way you can write this is unhappy element becomes happy element plus 4He2. Sometimes teachers will write alpha instead of He. Both work. It's just saying that we have an alpha particle coming off. Okay. Now let's think and consider beta decay. What happens in beta decay is we have our unhappy chemical, and a proton spontaneously becomes a neutron, which means that we lose a charge. Lose a charge, and more importantly, lose a proton. Remember, protons make elements. So what you'll see is that basically a beta particle will come off, which is 0 and 1. So if we have unhappy element, it'll turn happy, it'll get more stable, and we'll have a beta particle come off. So -1, and 0. If you're not familiar with this notation right here, where it's -1 and 0, I'll get into it a little more later when we do an actual practice problem. For now, just be aware that these kinds of things exist. We have another one that's pretty simple, relatively simple. It's called positron emission. And it sounds hard, but it's actually really simple. So I would say the single hardest thing is knowing what a positron is. I remember when I first heard it, I was like, what does that even mean? In layman's terms, basically, it's an electron, but it's positively charged. Super strange, I know, pretty abstract, wacky concept, but it's okay. Just accept it as fact and trust me. No, you can do some more research on it on your own time. I think it's a little heavy for what we're going over right now, but I think it definitely is really interesting to look at. So what will happen in positron emission is we'll have our unhappy chemical, and we will basically, it'll be like a beta decay, but remember how earlier it was a -1? It was -1 like that. This time it's going to be +1. So what we're going to have unhappy particle becomes happy particle plus +1. Okay, it's pretty fine and dandy, but now let's really quickly go over the last type. The last type is a little more confusing. It's called electron capture, and it looks exactly like beta decay. And I'll show you what I mean. We have our unhappy thing, and we capture an electron. And so when we write our formula, when we write a nuclear formula, it looks exactly like this. Sometimes teachers will have you write it the opposite way around, where this guy comes right here. But all in all, basically, it's beta decay. So what's even the point in learning what electron capture is, right? And that's just because there are two different ways that beta decay and electron capture function. So electron capture, this one I feel like is the easier one to wrap your head around, because electron capture is literally that. Your unstable chemical will capture and steal an electron into its nucleus. So it'll basically just abduct one. However, beta decay, this one's a little weirder to consider. Basically, a proton spontaneously becomes a neutron, losing one proton and transforming into a different element. Super wacky to think about and consider, I understand, but just bear with me. It'll be better. And if you have no interest in chemistry, then just take everything I say with face value and just move on. If you have interest in chemistry, Google it, look into it a little more, all of that, definitely it'll be great. So let's take, I know I'm beating this one to the dead, beating this one to the dead horse, basically beating a dead horse, but let's take carbon-14 one last time for one last spin. Carbon-14, it has 6 protons and 8 neutrons. This is way too many neutrons and will cause some sort of decay. In nature, you will really see it undergo beta decay, but just for practice, let's go through every single type of decay. So let's say it undergoes alpha decay. Well, you know that carbon-14 has 6 protons, and it's going to emit alpha particle, which is essentially helium, and that means that it's going to become a beryllium. And I really want you to notice how all of these top numbers are conserved, and all of these bottom numbers are conserved. So this guy plus this guy will equal that guy, and this guy plus that guy will equal that guy. Therefore, our nuclear reaction is balanced. Okay, let's do beta decay now. Beta decay is going to start the same way, but instead this time, because we're getting rid of a beta particle, our mass isn't going to change, but our atomic number is going to change. Oops, I forgot my E for beryllium, sorry. And I want you to notice one more thing. Notice how our element is actually changing every single time our atomic number is changing. Okay. So, oops. So far, so good. So far, so easy. Okay, let's consider a little weirder one. We have positron. I'm just gonna call it pos, but it's positron emission. We're gonna keep our same carbon-14, and what's gonna happen is actually it's gonna release not a -1 but a +1 beta particle, and what that's gonna be is now that we're gonna have boron. I sound like a broken record, but I do have one more thing you do have to notice. Notice the difference between this B and that B. This one is boron. This one is a normal B. This one is beta. It's Greek. It's a little special. Not saying anything like that, but just it's special because Greeks are cool. Okay, now let's go over the last one that is still super weird, and it's electron capture. And if you remember, I could save it for later, but if you remember, what'll happen is it'll look exactly like beta decay. And just for completionist's sake, I want you to notice one last thing. They're the exact same, right? But what's happening in beta decay? In beta decay, a proton becomes a neutron. In electron capture, we basically kidnap an electron, an E-. Okay, and I do want to note just one last thing when it comes to electron capture. Electron capture also will release an X-ray. Other teachers might say it's gamma rays, but gamma rays are honestly produced by all sorts, every single type of decay. So it's a little weird. I know I've seen some teachers, or at least I've heard from some students that I did tutor, that they say it's gamma rays instead of X-rays that come off. But the way I learned it is X-rays, so I'm just going to teach this X-rays and put a little note saying it might be gamma rays. I'm not sure. I think it's wrong, but it's always good to check your sources, So far, everything we learned about, super easy. Makes you even wonder why nuclear chemists are paid so well. Probably because of all the intricacies, and I don't want to cause like a war with all of the different like the nuclear chemist people, but just saying, why are they paid so well? Okay, so all of this was really easy. Let's move on to half-life. And I think the very best question to ask ourselves first is, what is half-life? So what is half-life? Half-life is the amount of time it takes for half of stuff to decay. Sorry, that looks so messy. Let me rewrite that for you. To decay. Say, for example, the half-life of the bananas is 12 minutes. And say we were starting with 100 bananas. In 12 minutes, we would be down to 50 bananas. And in 24, 25. Right? And this makes sense. So, from that example, what we can say is that amount of stuff A is equal to the initial amount we had, A sub 0, times 1/2 to the number of half-lives done, let's say. Right, and number of half-lives done is actually disgustingly long name, so I'm just going to call it n for number. How do we find n? Well, n is going to be, it's kind of obvious, right? We want to figure out how many half-lives we went through. Well, we're going to say how much time did we pass, t, all over what the half-life is, h. So if you want like a sort of a master equation, I guess you could say that a equals a sub 0 1/2 t over h. But, you know, just being aware of these two different formulas and kind of understanding what they mean is pretty crucial. Okay, so I think that's about all the content I do need to cover, but I did just throw so much at you, so I do want to do a couple practice problems. Yeah, let's take uranium-238. Uranium-238, right? So now this is more of a chemical that you would think about when you think radiation. Let's fix it up using alpha, beta, positron, and electron capture. Obviously, in nature, you're most likely to see not alpha radiation, alpha decay, just because uranium is so heavy. But you know, just for this little practice, I want you to be able to try be confident in doing it all. Here's another little fun fact that I thought I would throw in right now. It's basically, we're going to keep alpha decaying over and over and over again. We're going to keep alpha decaying over and over and over again until we eventually hit lead. And lead is considered like the last quote-unquote stable element. I just thought it was interesting to know, so I thought I'd share it here. So, I hope during my rambling you started it, and if not, I do want you to give it a try right now. Hopefully you get these. I'll solve them at the end. Okay, hopefully you tried it. I'm just gonna write down the answers right now, and I'll talk you sort of through it. But I don't really know if there's anything to be talked through, just because it's really easy. You know, this stuff is it sounds a lot harder than it actually is. So it's really just whatever on it, in my opinion. But oh shoot, what is next to? I know uranium usually goes to thorium because, you know, that's what everyone always thinks of. Pa, okay. You learn something new every day. 0 minus 1 beta. I wrote these so cramped. Gonna bring this guy down. Oh shoot. Probably should have thought about that, right? 238, 92, U becomes 92, 38, 93, Neptunium, plus 0, plus 1 beta. Remember that positron emission means plus 1. I'm going to highlight a couple things that I think you do need to know. Remember that this can also be 4 alpha. And then the last one, 238, 92, U becomes 238, 91, thorium plus 0 minus 1 beta plus a X-ray. This one right here may also be written, because it is capturing, I think this is a better way of writing it. I know sometimes some teachers, I was taught it this way, but I think it's better this way. It becomes 238, 91, thorium plus X-ray. Not thorium, I'm so sorry about that. I always just, whenever I see uranium, I think of thorium. Pa, there you go. Actually, I might have been taught it this way, and I'm just completely making that one up. So hey, it's a good thing that we're doing these practice problems, right? And so overall, super easy, super simple. Hopefully you get this, and remember that basically this chain right up here, let me highlight it for you so you know what I'm talking about. This chain right up here is going to happen over and over and over and over again until it eventually hits lead. You know, just most of the time it'll go to lead. If you're a nuclear chemist and watching this video for some reason, hello, feel free to berate me in the comments telling me how wrong I was about everything. I totally get it. I'm just trying to do, you know, help out people that, you know, can't really get the help they need. Okay, now let's try one last example. This time it's a Half-Life example, because I think Half-Life is really important to practice. I'm just going to do one just for the sake of time, because we are bordering half an hour and I don't want to bore people with like a really long lecture or anything. So let's practice it. So say we have a small crack in our room and radon 222 seeps into your room, right? It has a half-life of 3.8 days, according to Google at least. I'm not sure, I never came in contact with radon. How long will it take for 99% of the radon to be gone? And I chose this one because, you know, I just wanted to demonstrate for you how Half-Life can get involved with percent change and algebra and all sorts of these things. Another question they might have asked you is giving you like a time and asked how much is left. Actually, wait, I really like that. Okay, I guess we're gonna do two questions. Hopefully I don't bore you guys. So let's do this part B first. So we have some amount of uranium that seeps in, or not uranium, radon, A sub 0. We have that half-life is 3.8 days. And we left for, let's say, a total of 5 days. Equals T, I suppose. From here, we can, you know, figure out how much uranium, how many half-lives passed. Remember from earlier that we have that. Maybe I'll rewrite these formulas really quickly. Remember that we have that A equals A sub n times 1/2 to the n, where n equals T over H. If you need any definitions or anything like that, I did cover that in the earlier part of my video. And then from here, we can say that n equals T over H, which equals not 3.8, sorry, 5 over 3.8. So we can say that for how much is left, well, A equals A sub 0 times 1/2 5 over 3.8. And because we're trying to figure out how much is left, we can actually use a the percent change formula to, you know, figure it out. So percent change equals the absolute value of old minus new all over old times 100. Now this upper part right here, you know, I know I'm gonna have some purists or some people frothing at the mouth. How dare I say old minus new, not new minus old, or experimental minus theoretical or whatnot. It doesn't matter. Who cares? Just because we have absolute values, the math is gonna come out the exact same. So you'll be fine. Anyways, once we do end up finding the percent change, we're gonna have to say basically, oops, so sorry about that. I'm so sorry if you hear anything in the background. Someone's fire alarm in my college dorms just went off, so, you know, horrible. So percent change. Oh, I should probably finish off that. Well, just be aware that that's what I'm going to be plugging in for A. So this A right here is going to be new, and A sub 0 right here is going to be old. Just want you guys to be aware of that. So we're going to have old, the absolute value of A sub 0, minus, and then we're going to have A sub 0 times 1/2 to the 5 over 3.8 all over old, which is actually A sub 0 times 100. We know that that's going to equal A sub 0 minus, and then I just multiply everything out to get me about like what, 0.6? No, about 0.1 is that? Yeah, 0.1-ish. 0.1, and then a sub 0 divided by a sub 0 multiplied by 100. Using basic algebra, we can figure out that we'll have about 98%, sorry, 0.2, 98% gone, so we'll have 2% remaining. Super simple. Okay, now let's finally move on one last time, and let's do the other part. Oh shoot, that's not what I meant to do. Let's do the other part. Let's do the one last part. So, how long will it take for us to get down to 99%, right? Earlier we saw that it's 98%. But now we're going to figure out how many days we have to evacuate. Try it. I think you can get this, but I mean, if you can't, just continue watching. All right, so because we want to have 99% left, what we can say is that, or because we want to have 99% gone, we can say that we have 1% left, or that a equals 0.01 a sub 0, with a sub 0 being initial amount. We also know that a equals a sub 0 times 1/2 times x, or I'm going to call it t over 3.8, where t stands for a number of days. Right? Then we're going to just be able to substitute this a for that a. And we're going to say that 0.1 a sub 0 equals a sub 0 times 1/2 t over 3.8. Using basic algebra, we can cancel out the two a sub 0's, giving us 0.1 equals 1/2 t to the, or 1/2 to the t over 3.8th power. Using some log rules, we can say that ln of 0.1, or 0.01 is equal to ln, sorry, didn't mean that, t over 3.8 times ln of 1/2, or that t equals 3.8 times ln of 0.01 all over ln of 1/2. And that's going to come out to about 25 days, right? I'm going to be rounding and all of that, so it's a little long, but about 25 days should be what you have gone. Hopefully I didn't bore you out or like stretch this out too long. I just thought, these are a little important to know. So hopefully this was helpful, and good luck.